Okay, thank you, Chair, for introduction. First, I gotta say this is an intense title. Okay, I'll start with the reason why we conducted this study. First of all, methane is a greenhouse gas. And enteric methane is loss of feed energy. And typically, for lactating dairy cows, about 6% of the ingested energy is lost through methane during the carbohydrate fermentations. And this is how methane is produced from the rumen. So the microbes in the rumen require fermentable energy for their growth. So the carbohydrates from the feed are converted into volatile fatty acids with acetate and butyrate and propionate as the major three. And as you can see from this series of reactions, acetate and butyrate are considered to promote methane production because of the hydrogen produced during the production of acetate and butyrate, which are available for methane production, while propionate is considered as a competitive pathway for hydrogen utilization. And a scientist from Switzerland has proposed an equation to estimate enteric methane emissions based on the carbohydrate intakes. As you can see from these equations, the methane emitted from a unit of sugar intake is almost twice as much from starch. However, in that study, there's confounding due to the differences in chemical compositions of the diets. It's well known that the fiber fermentation is the major contributor to methane production, and the fiber fermenter require ammonia, which mainly comes from the rumen degradable protein for their growth. But little was reported on the effect of non-fiber carbohydrates on methane emissions. So this is what came down to this study. We want to quantify the effect of relative proportion of dextrose and starch at NFC source at two levels of rumen degradable protein on lactation performance and enteric methane emission. In addition, we want to determine whether the response variables are influenced by the interaction between the RDP level and the NFC source. And we hypothesized that a 10% substitution between dextrose and starch in the diets, with approximately 45% NFC in the diet, had no effect on lactation performance, and 11% RDP promotes lactation than a 9% RDP, and dextrose contributes more to methane emission than starch. This is based on the equation that I just showed you. And RDP level, as well as the interaction between RDP level and NFC, do not influence methane emission. So moving on to material methods. 18 mid-lactation hosting dairy cows were used in this split plot study. And the whole plot studied the effects of RDP levels. Since all diets have the same crude protein level, the 9% RDP diet has 7% RUP, while the 11% RDP has 5% RUP in the diet. And the subplot studied the effect of NFC treatment combinations with replicated Latin squares, and the cows rotated among the NFC treatment combinations, including DX, meaning 0% refined starch, 10% dextrose, and DXST, meaning 5% refined starch, 5% dextrose, and ST diet, meaning 10% refined starch and 0% dextrose. So this is diet ingredients. These three columns are the cows fed 9% RDP, 7% RUP, and with the different ND and NFC treatment combinations. And these are the three NFC treatments under 11 RDP and 5 RUP. So the proportions of all forages and corn grain are the same across diets. And by the utilization of refined starch and dextrose as the NFC treatment combination, we're able to avoid the confoundings caused by the differences in chemical compositions in the feed. And we utilized the combination of soybean meal, soy plus, and blood meal to reach our desired RDP and RUP level. So this is the chemical composition of the diets that we actually fed the cow. So as you can see, the crude protein level for all diets are virtually the same, and we successfully fed the RDP and the RUP levels that we desired. And the levels of starch and water-soluble carbohydrates is a reflection of our NFC treatment combination. And at the bottom, the levels of as-corrected NDF and non-fiber carbohydrates are very similar across diets. So for sample collection, methane was collected for each of the 18 cows at 11 different time points during the third week of each period with the green feed unit. And when I want to take a sample of the methane of the cow, I will remove the feed in front of the cow and I push the cart towards the cow. You cannot see the head of the cow because she put her head in the feed trough of the unit and consumed concentrate mix. While she put her head in there, the machine draws air from the breath of the cow and it continuously measures the concentration of the methane. And plus, when we know the airflow rate, we're able to estimate the methane emission based on that spot sampling. And additional response variables that were collected include daily dry matter intake, milk production, and milk composition. And for ruminal variables, we collected ruminal pH, ammonia nitrogen concentration, and VFA profile through ruminal synthesis procedure during the fourth week of each period. All data were analyzed through product mixed procedure of stats, and the model included effects of RDP level, NFC treatment combination, the interaction between the two, period, and RDP by period interaction. In addition, orthogonal contrasts of linear and quadratic effect associated with NFC treatment combination were tested. And significance was declared at p-value equal or smaller than 0.05 and a tendency between 0.05 and 0.1. So for results, for performance, production performance, we'll first take a look at dry matter intake. On the axis is the NFC treatment combinations, and the response variables is the dry matter intake. And as you can see, there is a significant NFC effect that as the starch increase and dextrose decrease in the diet, the dry matter intake responded both linearly and quadratically, with the greatest dry matter intake achieved for cows fed DX and DXST at about 24.4 kilogram, while the lowest dry matter intake achieved for the cows fed ST diet at 22.7 kilogram. And for milk production, there's a significant effect that so on the axis are the different RDP and RUP levels of the diet, and the cow fed 9% RDP, 7 RUP had greater milk production and fat and protein correct milk production than cows fed 11 RDP and 5 RUP, and the gap are approximately 2.5 kilogram per day. And for feed efficiency, which is defined as fat and protein correct milk divided by dry matter intake, there's also a linear effect on the NFC treatment that as starch increase and dextrose decrease, the feed efficiency increased linearly, with the highest feed efficiency achieved for cows fed ST diet, which is 10% refined starch and 0% dextrose, at 1.58. And for milk composition and yield, as highlighted in the boxes, cows fed 9% RDP, 7% RUP had greater fat and lactose yield than cows fed 11% RDP and 5% RUP. And for rumen metabolism, there's a significant effect on ruminal ammonia nitrogen of RDP levels, that the cow-fed 9% RDP, 7% RUP had lower ruminal ammonia nitrogen than cow-fed 11% RDP and 5% RUP. And the gap is somewhere around 5 milligram per deciliter. And for VFA profiles, there's no differences among the molar proportion of acetate and propionate among diets. However, there's a dietary effect on molar proportion of butyrate. That as starch increased and dextrose decreased in the diet, the molar proportion of butyrate decreased linearly and responded quadratically too, with the lowest molar proportion of butyrate achieved when cows are fed ST diet. And last, let's take a look at the enteric methane emission. So there is a significant NFC effect on daily methane emissions, that as starch increased and dextrose decreased, the daily methane emission decreased linearly, with the cows fed ST diet had the lowest methane emission. However, when methane emission was expressed on the diameter basis or methane milk or fat protein correct milk basis, there were no differences across diets. So for discussion, I want to talk about 2 points. First, the effect of NFC treatment combination on daily methane emissions. Raman and Hooten proposed an equation to estimate methane production based on dry matter intake. So the more dry matter intake, the more methane produced for the cow. And in our study, we observed the same trend of methane production and the dry matter intake production. So the cow ate less and the cow produced less. And in our study, when the methane production was expressed on a per dry matter intake basis, there were no differences among the treatments. So the treatments, the methane production differences among the NFC treatment combinations are mainly caused by the differences in dry matter intake differences. And the second point is the effect of rumen VFA profile on methane emission. At the beginning of my study, at the beginning of this presentation, I talked about butyrate along with acetate. I thought to promote methane emission because of the hydrogen produced during this VFA productions. And in this study, we detected higher butyrate molar proportions for cows fed ST diet, which had lower methane emissions. So the differences in molar proportion of butyrate also partially helped us interpret the differences in methane emissions. So to conclude from this study, the cows fed 9% RDP, 7% RUP had greater lactation performance than the cows fed 11% RDP and 5% RUP, with approximately 45% NFC in all diets. And cows fed 10% refined starch had lower dry matter intake and emitted 7% less daily methane than cows fed 10% dextrose, without change in milk yield. And methane per unit of dry matter intake or per unit of fat protein correct milk was not affected by the dietary treatments. With that, I'd like to take any questions. Thank you.